Uh, so we are happy to have Roji. He will tell us about theory dependence of black hole interior reconstruction and improved strong subadditivity. Roji, please take away.
Just keep it here. Yeah, thank you. Yeah. Hello? Okay. All right. Thank you. Thanks for this opportunity. I'll be talking about the theory dependence of black hole interior reconstruction and the improved strong subadditivity. And improved strong subadditivity. I will write ISSA. Yeah. Bit down. Bit down? Yeah. Sure, sure. This is fine, right? Should I write it down? Oh, it's fine, sir. Okay, I will do that. Thank you. So consider an evaporating black hole. So this is the Penrose picture of evaporating black hole. So assume that the black hole is formed by the collapse of matter. Then any black hole will evaporate. The radiation will go to the sky plus. And this is a thermal radiation. So once you compute the entropy of radiation collected at sky plus, assume that the time at the boundary is u, then this is a function which is monotonically increasing with respect to time. So here you have the entropy, and this is the time u. So the radiation entropy just keeps on increasing. But at the same time, the black hole is evaporating. So the size of the black hole horizon is decreasing, so that the Bekenstein entropy of the black hole just comes down. So this is the radiation. So the Bekenstein entropy is also a function of u. Now at some if you assume that the entire state of the black hole, or if you start with a pure state, then it should be having same entropy for radiation and the black hole. And we know that the black hole von Neumann entropy should be less than or equal to the classical entropy, S Bekenstein. But here we have a calculation that says that the radiation entropy just monotonically increases. So there is a time at which the entropy of the black hole, or the Bekenstein entropy of the black hole, becomes same as that of the entropy of the radiation. So this is the phase time. So after this time, it's clear that the radiation entropy is not equal to the black hole entropy. So this is the unitarity violation. You started from a pure state where you had this equality, and then you end up with a state which doesn't satisfy this equality. So you have a unitarity violation. So at least for evaporating ADS black hole, we have a proposal, or we know that how to resolve this issue. So the proposal is that, which is the Island proposal, you replace the radiation entropy with the generalized radiation entropy. So here what you do is, so this is something which you which you thought to be equal to the reduced density matrix for radiation. Let's say rho is a reduced density matrix for the radiation. Then we thought that the entire entropy of this reduced density matrix is given by S radu. But the Island proposal says that no, it should not. You should be replacing it with the generalized radiation entropy. So how do you get this? So the proposal is that you have this black hole. So the proposal is that some of the interior of the black hole or some part of the black hole geometry will belong to the radiation, so that when you compute the entropy, you should be computing the generalized radiation entropy by including the gravitational contribution, the area contribution. So let me call this as the island that belongs to the radiation at scribe plus. So you have to include the gravitational piece, which corresponds to the boundary of this region, the gravitational region. So compute the value of the or the area of the point, which is the boundary of the island, and compute the radiation entropy or the von Neumann entropy by including the contribution from matter that is there in the island. So you should be computing the entropy of matter that is there in island plus the Hawking radiation that is at scribe plus. So you calculate this generalized entropy by minimizing the generalized entropy with respect to the island boundary or the island. So this quantity, the claim is that this is what computes the actual entropy of the reduced density matrix for radiation. If you replace the naive entropy with generalized entropy, then the claim is that this will restore the unitarity. That means S generalized radiation entropy will be equal to S generalized entropy for black hole. Okay. This is the proposal. So this means that after this phase-time, radiation at scribe plus will have access to the inside of the black hole. So you can reconstruct the interior of the black hole, or the degrees of freedom that belongs to this region, belongs to the island, can be reconstructed from the Hawking radiation at scribe plus. Right. I will come. Yeah, sure. Sorry, always?
Always reconstruct the interior of the black hole. I mean, if you draw the ADS diagram, it will become clear. If you draw the ADS diagram, inside of the black hole, you can get even before the page time, because everything is at the boundary. It's true that at later time, some part of it is going to the power. You can always get the inside of the black hole, even if you didn't have evaluation.
Even if
this would be important.
Yeah. So here the point is, I want to construct it from the radiation. Yeah.
You can still reconstruct the media just from even before that speech. The page time is not of relevance for reconstruction. Why is the page time of relevance for reconstruction?
No, I just want to reconstruct from the radiation, right? From the future radiation.
You don't want to go from the I plus to this, right? You want to go from the past to there, right?
Yeah, from here to here.
No. What interval are you taking on scribe plus?
So here?
No, on scribe plus, is it that curly bracket? You're taking the interval from scribe plus minus to that point, right? That page time point.
Yeah, so from here to here, right?
Yeah, but you can reconstruct the interior even before that page time. For the question of reconstruction, because you can always do the reconstruction even from near spatial infinity.
From here?
Yeah, just from there. That's right. You just need a small interval there to do the reconstruction. So the page time is not relevant if you only want to ask questions of reconstruction. Maybe it's not important for what you're going to say, but.
So my concern is about the radiation, just from the radiation that is collected. Like in my case, like it will be the usual ADS black hole where you have a non-gravitating bath. So maybe you're saying that the asymptotic algebra, are you trying to use that?
Algebra, right? I mean, and you can look at some subsector which doesn't have gravitational degrees of freedom or something. But if you just wanted to reconstruct, you could reconstruct it from the past also, right?
So at least so here I thought I'll be talking about the ADS case. I don't know, when you have a non-gravitating bath, whether you're asymptotic.
Okay, so maybe if you draw non-gravitating bath, it will become clear. So if you just draw the Penrose
diagram. I will draw it. So so let's say you have the so maybe I'll just state my aim, like what I want to do. So for the ADS black hole, let's say for the evaporating ADS black hole, the usual models are JT gravity black hole coupled to a bath. Right? Now the radiation that is going to bath. So from that radiation, can you reconstruct the interior of the black hole? Right? So this, my understanding is that after page-time you can do the reconstruction.
Right, because the bath is non-gravitating.
Exactly.
But if you take the complement of the radiation region, which includes also the boundary, then you can always reconstruct part of the interior, right? Even before page-time.
So you mean, so just say let's say,
just exactly
the usual black hole.
Yeah,
right?
and don't even add a bath. You can still reconstruct.
Exactly. Even in that case, the statement is that the region that belongs to the entanglement wedge of the boundary theory can be reconstructed, right? So that is one thing. Like I will come to this particular picture. So here I am considering a situation where this black hole is coupled to a bath. Let's say to begin with, start with a bath having 0 temperature. So in that case, the black hole will evaporate, right? Now that evaporated radiation will be collected at the scriptless of this bath, and from that radiation, can I do the reconstruction? So this is possible after page-time. Because after page-time, the entanglement wedge of the radiation at scriptless will contain the interior of the black hole. Right? Now, the thing that I would like to ask is the following. So, this reconstruction of black hole interior from radiation. So, this reconstruction, what is the theory dependence of this reconstruction? That means, do you really require to know the entire coupling of your theory, for instance, to do the reconstruction? For instance, you can ask, do you really require the full quantum gravity to do the reconstruction of the interior of the black hole, especially say region near the singularity or slightly away from the singularity? Do you really require a quantum gravity, or is it enough to have some ensemble theory that might be dual to this boundary theory? So how much of the how much dependence is there for this reconstruction in your specific details of the theory? Like so this is the thing which I would like to understand. So do you really require quantum gravity to know the singularity structure of the black hole? So let's say there are two possibilities. One possibility is that you do the reconstruction from the radiation collected at the boundary. Then if that reconstruction doesn't really depend on the details of the theory, then you can interpret in the way that you collect the radiation, and from the radiation you can construct a protocol that gives you all the couplings of your boundary theory. That means you can determine your quantum gravity from the radiation that is collected. Or it may happen in the other way. You really require to know the full quantum gravity to do the fine reconstruction of the interior of the black hole. So I will make it more clear. At least the statement is that, do you require to know the full detail of your theory, boundary theory or the bulk theory, for reconstructing the interior of the black hole near to the singularity from the Hawking radiation which is collected at the scriptless, at least in this model. Sorry? No, the point is that final answer will be that you really require the full detail of the theory. How is that? How can you see it? Like than just by saying it. Can you come up with a criteria that tells you that if that criteria is satisfied, you don't require full quantum gravity. If that criteria is not satisfied, you require the full quantum gravity to do the reconstruction of the, right?
There's some radiation which comes out.
Yeah.
It's just highly scrambled.
Yeah.
And the precise details of the scrambling, if you really want to construct the initial state,
Yeah.
it require you to know all the physics.
Right.
If you didn't know all the physics, you would not be able to do it.
Yeah. So at least anyway, that's the final result I also have. So there is no contradiction. No, actually, the point is that you have an intuition. We have to check it, right? At least we have to properly state it and see how to maybe how to get that result, whatever you are saying, your intuition, whether your intuition is correct or not. Right?
For simpler things, you already see chaos in a black hole diagram. Here you're doing something much more complicated. You're allowing the whole system to evaporate. You're asking, can you get initial state?
Yeah, so I will come to a simpler setup. So this is the full setup. Like you should allow the black hole to evaporate, and then the black hole will disappear, and then collect the radiation and see whether you can do the reconstruction with or without the knowledge of quantum gravity. Okay, that is the full setup. Now, like you said, there is a back reaction involved, the geometry changes. So I would like to go for a simpler setup where I don't have to really deal with the back reaction issue. So instead of considering a bath having temperature 0, we can always consider a bath having temperature same as that of the black hole. So you can start with an eternal black hole in ADS. All the degrees of freedom inside the black hole.
Because it's possible that maybe if you were wanting to some expectation value of some operator or something, maybe that you can reconstruct more easily.
Yeah, I want the operators, like by following say HKLL or some more complicated thing.
Or the correlation functions, that's a bit harder.
Yeah, so
reconstruct even out of time.
Right. Yeah.
But so when you say reconstruction, what is it that you want to reconstruct?
So let's say you have a dressed operator that is inside the in the gravitational region. So we have the reconstruction protocols or proposals how to do the reconstruction, right? Let's say with the simpler cases, you use the HKLL, dressed version of HKLL. You can express an operator in the bulk in terms of the operators in the boundary theory. So if you know that, then you can construct all the correlation functions, right? So I'm looking for a fine detail, not sum of the expectation value.
Okay. So you want to be able to calculate correlation functions of bulk objects.
Right.
So, earlier works, usually people say if you want to work with the horizon, you want to ask if the horizon is smooth, which is a simpler version of bulk. And then you can kind of proceed. It's a little easier because then the horizon tends to become smooth by the low head here because things tend to fall in.
Yeah.
But if I understood you're saying that you really want to construct everything in the interior, even the other singularity.
Yeah.
So that means that you see for the kind of question about the horizon, you can kind of keep track of what's happening outside.
Yeah.
But here you want to ask, let's say 10 billion years ago, either an electron fell in or a muon fell in. I want to know whether it was an electron or
Yeah, right.
Okay, but is there any hope that you would know that without knowing the details of the theory of the dynamics?
No, I don't know. Like I just want to make it precise, right? Than just saying that there is some intuition, because it's something which is doable. I won't consider the setup where bath has 0 temperature right now. I will consider a setup where bath has temperature equal to the black hole temperature. Okay. So in this case also, you have a Hawking-like paradox. So the black hole anyway will emit Hawking radiation, and the Hawking radiation will go to the scribe plus of the bath. So this is the Hawking radiation. At the same time, since there is an equilibrium between black hole and the bath will send equal amount of quanta to the black hole. So this is the bath quanta. So the bath radiation compensate for the Hawking radiation that went to the scribe plus. So the advantage is that since there is no net flow of energy across the boundary of the ADS region, the geometry of the black hole will be the same as that of the eternal black hole for the entire evaporation process. Like this is not going to completely evaporate away. You will always get back same amount of energy. So effectively there is no back reaction. Classical geometry is going to be same for all time, all boundary time. So this makes this setup more attractive or simple for calculation purpose. But you still have an information paradox. So since there is an exchange of Hawking radiation and bath radiation, there will be a growing entanglement. between bath and black hole. So the left right of the black hole and the left right of the bath, they start entangling, and you can compute the entropy of bath for some time, some boundary time u. You will see that this entropy is linearly proportional to the boundary time. The entanglement entropy between black hole and bath linearly rises. So at some point you reach a situation where the bath entropy, say at some phase time, bath entropy is equal to the constrained entropy of the black hole, the two sides of the black hole.
Connect the bath at some finite time.
Yeah, at u equal to 0.
The way you have done it, you have connected it finite.
Yeah, it looks like so. So you have to actually connect it at u equal to 0. Since there is time reversal symmetry, I'm just drawing it this way. Otherwise, you should be drawing it this way, right? Like in the usual evaporation setup. Since there is no energy difference, you don't have to send additional shock, right? So if you want the black hole to evaporate, you have to send a shock, right? Like, sorry?
In setups, usually I think you assume the bath is coupled for all times. You don't try to turn on the coupling anyway. If you decide to send a shock.
I mean, then you could think that I mean, this just like just changes the point of reference, right?
No, it's just that state. There's some negative or some philosophy here. Coupled to a bath, everything is in equilibrium. That's it. You never couple the bath.
Yeah, that's. I mean, if you want to start your then the point is that the boundary time reference you keep at very early time. So where you start like the. I mean, the point is that at u equal to 0, by that time itself, you already have a lot of entropy growth, right? If you had coupled a long time back.
You see, the entanglement entropy grows both in the future and in the past. So at this, in what I'm saying, the equal to 0 slice is a slice where you have minimum entanglement.
Yeah.
Both towards the future and towards the past, you have a back. So it's not that only towards the future. The entanglement entropy is time significant.
Right. That's why I'm saying at u equal to 0, like maybe it doesn't. It's not going to change any of the analysis. Like you can think of this as something which is coupled at u equal to 0, or you can think that it was always coupled.
I think you have to think of it as being always coupled.
I mean, it doesn't matter. Like if you want to think in that way, that's fine. Because anyway, I'm going to look at the system after some time. Yeah, I'm not going to look at the system starting from u equal to 0. I want to look at after a long time. Yeah, that's fine. So I can, I mean, if I send it, then I will have a shock wave, right? You mean goes this way? I mean, then even then I can ask, okay, at least this portion, can I do the reconstruction, which is outside the shock wave? Okay. So anyway, at some point, the entropy of the bath becomes equal to that of the entropy of the two-sided black hole. So beyond that time, you have a information problem or a unitarity violation. So you can again solve the problem by replacing the bath entropy from the naive entropy to the generalized entropy. Again, by introducing an island for the bath, just like in the case of evaporating black hole. So you have an island for bath after space-time. Okay. Now I want to understand if I want to construct a degree of freedom that is living inside this island from the bath radiation, how much details of the theory is required? Let's say I take this island very close to the singularity. So then the degrees of freedom that is living near the singularity, in principle, I should be able to construct from the bath radiation, right? So how much details of the theory or how the details of the theory is going to affect this reconstruction? So to make this statement clear, what I will do is I will introduce an additional theory into this setup, a CFT2. Like initially, I have a CFT living in the gravitational geometry and in the non-gravitating path, so which I call a CFT1. CFT1 is a CFT having transparent boundary condition across the boundary of or the interface between bath and the black hole. And now I introduce one more CFT, a CFT2, which has reflecting boundary condition at the boundary of gravitating region. And what the speciality of or the property of the boundary conditions is that these boundary conditions are drawn from a distribution. Fields in CFT2 are drawn from a distribution. That means you have random boundary conditions. No, I just mean, so this is the gravitational region. The JT gravity is ending here. Then the bath, exactly. So I want to introduce a CFT2 which has a property that all the matter fields in CFT2 will be reflected back when it reaches the boundary. Yeah, CFT1 is there, that has a transparent boundary condition. So CFT1, so the field in the CFT1 is the one which is evaporating to the sky plus, which crosses the boundary, and the same CFT1 will have degrees of freedom in the bath region that will be going to the black hole. So the CFT1 degrees of freedoms are getting exchanged. That's why there is an entanglement between the bath region and the black hole region. But for CFT2, that doesn't happen. All the matter field will be reflected back to the gravitational region. But the only thing is that the boundary conditions of the matter field in CFT2 are not precise. Like we haven't specified it completely. We say that one particular boundary condition comes with a particular probability. So for instance, we can consider a simple free CFT having C2 number of bosons. And CFT1, let's say it has central charge C1, and CFT2 has C2 number of free bosons, and it's a free theory with action given by 1 by 2 pi alpha prime del xi del bar xi. I runs from 1 to C2. And so the entire geometry of black hole and the bath can be thought of as a part of a plane called W plane. So if I take this plane and look at the right and left Rindler wedge, so let's say I look at the right Rindler wedge, this portion can be understood as the union of right side of the black hole, the right side of the black hole, and the right side of the bath. Similarly, the left side can be thought of as the left Rindler wedge is union of the left side of the black hole and the left side of the bath. And here you have a cutoff where you have the black hole singularity. So the usual coordinate that we have for the right side of the black hole can be written in terms of the coordinate of the coordinates in the bath region. Let's say the flat space coordinate in the bath region is y plus and y minus. Then the metric of the black hole outside the horizon is given by minus 2 pi beta whole square dy plus dy minus sine symbolic square pi beta y plus y minus. Okay. So this entire right side can be fitted into this W plane by using the coordinate transformation W plus minus equal to plus or minus e raised to plus or minus 2 pi by beta y r plus r minus, sorry. So this is for the right region, right side of the geometry, and for the left side of the geometry, this is given by minus plus e raised to minus plus 2 pi by beta y l plus minus. This is for left side. So in this W plane, you can have the full geometry. So the calculations will be simple if you're working with the W plane. Now the metric of the black hole will look like, it takes this following form: 4 into dw minus dw plus divided by 1 plus w plus w minus square. It's basically the Poincare disk. Okay. So when we do the calculation, we'll be using this W plane.
No one who's done all these calculations. The question is as follows. What you're doing, you're assuming there's some CFT.
Yeah.
And then you're trying to make this conformal transformation. Actually, the CFT in the bulk has both. There are two things. First, I guess in doing this, you're ignoring gravity in the bulk. And you're assuming you can treat the CFT state separately because you're going to treat the CFT and then the other issue is that there's a non-normalizable mode that goes in the bulk, which is actually growing towards the boundary of things. I mean, there's some. When you quantize the CFT, because you have these transparent boundary conditions,
Yeah.
you also have a non-normalizable mode.
Yeah.
Now, that actually it's a little bit of a problem for defining the CFT in areas. And roughly the reason is it creates a problem for defining the measure in the path. And you know, if you go back to the analysis where the while anomaly comes from, which is because you're going to use the while anomaly here. Right?
Yeah.
It comes from defining the measure which goes like saying normalizing the path integral by saying e to the minus square root g phi squared equal to 1. Equal to d phi e to the minus square root g phi squared equal to 1. In this case, that integral is not well defined. You want to define orthonormal modes, but with these non-normalizable modes turned on, defining orthonormal modes in ADS is difficult because the integral of square root g phi squared doesn't converge in ADS.
So when I do this entropy calculation for a region, say here, a region in the bath from the left and the right side bath, how that will be reflected?
Conformal translation. So this CFT, before you define the theory as a quantum theory,
yeah,
so you have to define what it means with this non-normalizable mode.
But in the entire plane, like let's say I'm just thinking of this as some plane, and there.
Start with ADS coupled with flat space, and then you want to make a wire transformation.
Yeah.
You can't start with, I don't know, maybe you want to start with, if you want to start with ADS coupled with flat space.
So like you said, like if the coupling was between bath and the black hole was done like some time in the past, then like it was, this geometry was there forever, right? Like yeah, so I have to have this 1 by epsilon square.
On the left.
On, yeah. Here?
Oh, you want to put there also 1 over y.
Yeah. Otherwise, it won't be a smooth gluing, right? The metric should not jump across the glued geometry.
Now the metric. Now I would have thought you have the problem on both sides and define this area.
No.
Because there's this point where the metric becomes singular.
Yeah. So actually, I have this scaled flat space with 1 by epsilon square. Yeah.
You see, you want to define the theory on this space.
Yeah.
And then you want to make a singular wire transformation. Define the theory on flat space, right? Which will just be that metric summation you go to.
Yeah. So this is for the black hole region, the W plane, this metric. Okay, and for the flat space, I still have this 1 by epsilon piece coming. I still have 1 by epsilon square, because anyway this 1 plus w minus becomes epsilon near the boundary. So yeah, right, and then attach the bath, which has this 1 by epsilon square in the metric. Okay. I mean, this is the calculation done by Maldacena. Like the main difference is that I introduced one more CFT in the gravitating region, which has reflecting boundary condition. And so the CFT is so simple. It's just C2 number of the bosons, and it's a free theory. And when I say that I have a random distribution of boundary condition, what I mean is the following. Take the field xi and say that the boundary condition of this field at the ADS boundary is ji. Okay. So the probability for the field xi to have this boundary condition ji is given by some distribution. So I will take the simple distribution, the Gaussian distribution. Yeah. So it's given by delta by 2 pi e raised to minus delta square by 2 ji square, where delta 1 by delta is the standard deviation. So I assume that the field xi to have boundary condition ji is given by pji. Okay. So this is the randomness in my bulk theory. So we expect that if you have a boundary theory for it, the boundary condition will become the coupling, and then the coupling will have randomness. So your boundary theory will be an ensemble average of theories having couplings drawn from this distribution. Okay. Sorry?
The other CFT, C1 CFT.
Yeah.
Is it also free theory?
Yeah, it's a conformal field theory. No, I don't have to assume that's a free theory. It can be a more general field. No, so there are two CFTs. One is CFT that is living in bath and the black hole, which has transparent boundary condition. That is not free CFT. That can be a generic CFT. Because entanglement entropy calculation for a generic CFT is simple, right? For this plane. So I don't have to assume anything. For this case, I have to do a little more computations. So if I choose a free CFT, those computations will be simple. But anyway, I'm not going to lose any physics insight. It doesn't matter whether I choose a interacting CFT or a free CFT. The main essence is that the boundary conditions are drawn from a random distribution.
Actually, when you're saying you're going to reconstruct correlation functions, you construct correlation functions in terms of primary C1 CFT. So you need to know the primary spectrum.
Right. Sorry? Yeah, so I won't be doing this construction. What I will do is I will compute the entanglement wedge associated to this random distribution. I'm not computing observables. So this is like seeing in principle, is it possible to construct or not? So if you have a non-trivial entanglement wedge for the random coupling, which I will say how it will come. If that is there, that means that region of the gravitational region will be controlled by the random coupling. Only if you specify the coupling, then you can reconstruct that. So I will specify that, like what exactly I mean by it. Sorry, it is for the bulk field, it's a boundary condition. So if you look for a boundary theory, if there exists a boundary theory, then these boundary conditions will be like a coupling. No, that is for CFT1. I introduced one more CFT, which is a CFT2, which is restricted to the gravitational region. It's not going outside, or it's not going to the bath.
It's only coupled through this.
Only coupled through the gravity.
So the boundary.
There's a CFT2, which is this one for which you're doing S.
Yeah, this is for CFT2. It doesn't live in bath. Yeah, it is only living in the bulk.
Oh, I see. So everything else lives both in the CFT.
Yeah.
But you added one some additional degree of freedom.
Right.
Which is living only in the bulk.
Only in the bulk.
Gravity also
Only in the bulk.
Only in the bulk.
Right.
This lives only where the gravity lives. This lives only where gravity lives. And
Exactly.
This one doesn't have transparent.
It doesn't have transparent boundary condition. Yeah. So if there is a dual then that would be like you have a CFT, boundary CFT coupled to some reservoir, boundary reservoir, and the CFT dual to this geometry is actually an ensemble boundary CFT, because all couplings are not known to you; they're drawn from a distribution, right? So, and you have an ensemble average theory coupled to a bath in the boundary.
Now, why do you say the coupling is like a source? GI that you
No, this one in the bulk theory, it is just a boundary condition. It is a boundary condition, nothing more. Actually, I'm not going to do any explicit boundary calculation, boundary theory calculation. My calculations will be a bulk calculation. Right, with this distribution. Right. This field xi can have boundary condition ji with this probability.
Why is that differentiated?
Sorry?
Why is it differentiated?
Because the boundary condition you have to make. Sorry.
What I'm asking is, you don't want to make different variants.
No.
If you don't, you see, but that should only be specific. Yeah. There are different kinds of rifts in the bulk. One of them is also radial rifts, and the other is rifts along the boundary.
Yeah.
To get something that's invariant under both radial and means that this function on the boundary should be if and while invariant. And this guy, I think, is not if and while invariant. Like just adding something to this.
Putting a boundary value for the coupling. Yeah.
You need to write down something that looks like J of E1, J of E1 minus T. Integrate over T1, T2, when T is the boundary dimension. So maybe we can have J is a function of
J, like right now I'm taking this to be some constant, some Dirichlet boundary condition. No, it doesn't change with T. It does. It's not dependent on the boundary time. So it's just some number. So Dirichlet boundary condition for the CFT. Okay.
There's a radial diffeomorphism in the bulk.
I see.
Which you don't want. You see, when you pick the boundary, there's always a choice of conformal factor, right?
Yeah.
That choice of conformal factor translates into wire transformation.
Mm-hmm.
So whatever you do, you don't want to break that wire transformation of the source of the boundary.
So let's say I have a pure an internal black hole which is not coupled to bath, and I introduce this CFT there. Is it allowed for me to have this boundary condition?
I mean, you're allowed many things, but if you this boundary condition and then you do something bad to the gravitation, so you're kind of breaking the different variance. But the weight is not like a gauge. It is in the bulk, not the CFT. In the bulk, so in the frequency is the gauge of gravity or the CFT. So only variance is not gauge boundary. No, in the CFT, you never first of all actually are allowed to see. Here it's like turning on an operator. Let me say that it's like turning on an operator. In the CFT, you just kept it there. If you do that, that will break the conformity. Then you won't remain in this. Maybe that's another way. Sure, but
Now this is just saying that I'm not introducing any particular sources. This is the boundary condition for the field for all time.
yeah. So in the CFT, it's like just adding some term to the action. That operator is not an exact. That operator will.
Now, if there is a change in the boundary condition, I have to introduce an operator at the boundary. So that's why I'm saying this is not time dependent boundary condition. So if I say that, let's say for time less than 0, I have one boundary condition, above 0 another boundary condition, then I have to introduce an energy difference, right? This like changing the Dirichlet d brane, I have to move. So for that I need to introduce equal amount of energy that is required for changing the boundary condition. Here I'm not going to change the boundary condition at all. For a field I fix it, but that fixed boundary condition is drawn from a distribution.
I think maybe what Sukat is worried is that this xi may not be a dimension 0 object, right? So it's not violent variant.
So xi minus xi by alpha square root of that's
You're saying it's exactly marginal. The operator corresponds.
yeah.
Yeah. Because it's
Xi is a bit tricky of a logarithmic.
yeah, but you consider only del x as the operator. X
He
is
wants
not
to
a
put a
good
boundary
operator.
condition X.
I know, but it's not a. But it's not in the spectrum. That operator is not in the spectrum.
Yeah, but I don't know, like, what would be the boundary condition even allowed? It is a law,
It's like going to Coulomb branches.
actually, x equal to j is like a boundary condition that doesn't break conformal invariance. Right?
That
Doesn't break conformal
Yeah.
invariance. Yeah, so you know something like
X equal to G. If there's some log Z grows and you say log Z is equal to G.
like a G point. They're saying it's like a Debrien boundary.
it is a deep brain boundary condition. Yeah, that's why I'm saying if I make it time dependent, then I have to provide energy to change it. Like let's say beyond u equal to 0, in the past if you have J1 and in the future I have J2, then I have to add a boundary condition changing operator at the boundary. Then whatever you're saying is correct.
If you do that, you might end up fixing the bulk graviton. You specified some it's not maybe you do that, but you might end up fixing the bulk graviton. Maybe that's okay.
I mean, when you have a stack of deep brains and you move one of them, don't do anything to the
that shift they started. Yeah, the aging X will be like having a deviant move.
Yeah.
Yeah, you have to be careful about it.
not time dependent. I mean, time dependent. You just separate out
Yeah,
one of
that's
them.
Okay.
Analysis speaks, it's not allowed to move according to that. You kind of specify it. I think if you
Yeah,
do
you
it, you
specify it.
specify the features of external source.
Yeah.
Then I think that would not be something not. You just have the CFD, I guess.
I mean, this is like anyway. I'm doing this analysis for JT gravity, like in 2 dimension, which doesn't have any explicit graviton in it. So it's just the JT gravity coupled to.
There's some path integral you don't want to if you're not getting path integral. You want to do the integral metric to get RA.
I mean, the metric in the sense basically, I mean, whatever theory you have, that will tell you what is the dilaton profile, and that itself tell you what is the geometry, right? And what is left is just a CFT path integral. There is no real, like, other than the, I mean, like summing over all wormholes, you don't have any non-trivial path integral for the gravity part. It's just a Schwarzian, right? Exactly. Whatever you have is the boundary degrees of freedom because of the cutoff. Boundary condition. So whether this is conformal. X equal to J, like I haven't checked it. Yeah. So I'm just taking this to be like. I mean, I haven't thought about like whether there could be any non-triviality, because I thought this is like putting a different condition. I mean, anyway, this is the same analysis done by Almeri and Lin, where they exactly use the same boundary condition, like the same traditional boundary condition. Whenever you change the boundary condition of the boundary, you have to add a boundary condition changing operator, which has a dimension exactly equal to the de Bruijn energy change.
Yeah, I mean, this is something I generally worry about in entanglement. People are not be careful about it. Usually, when you add NDC, you don't fix the boundary and you get the hand and allow you to just whatever you like. That should go. But they maybe not just.
Okay.
For instance, one problem would be that one charge gravitational interaction this operator would not be exactly matched. So it would cause the CFT to run and you would not have.
No, yeah. So what I am assuming is that like the non-trivial thing that is in the bulk theory is the dilaton. I'm not coupling the dilaton to the CFT anyway, like so that I can keep the geometry of radius 2 always like the pure radius 2 geometry.
The metric is coupled, right? You usually have a square root G something. The dilaton will couple to this.
Right, but like if you try to solve it, since it's a reflecting boundary condition, then since there is no net flow of energy, the general solution will not be affected by this CFT2. It's time independent.
That's why it says.
Yeah.
It's a flat direction.
Right. Anyway, once you have this randomness in the boundary condition, the reduced density matrix for the black hole can be understood as a mixture of states. Anyway, since there is a bath already, even if you fix the boundary condition, you have a reduced density matrix. It's not a pure state for the black hole, since the black hole is coupled to bath. And on top of it, since there is an uncertainty in the boundary condition, the reduced density matrix for the black hole is a mixture of reduced density matrices having different boundary conditions. So rho black hole J1 to J2 is the reduced density matrix of the black hole with boundary condition J1 to JC2. Okay, and this comes with the probability square root of P J1 to P J C2. Sorry, why is? Sorry, not square root. It should be for a state. It should be square root. This is and then sum over the boundary conditions. Now, if you want to purify this state, it's not enough to have the bath Hilbert space. You also require to add one more reference Hilbert space. That I will call. So you have to. You can purify the state by taking the product of black hole Hilbert space, bath Hilbert space, and then one more Hilbert space, which I call a journal Hilbert space. This is a reference Hilbert space, which takes care of the boundary conditions. I just call it journal. I mean, again, I'm following the journal. So you have a journal from which you read out your coupling values, okay, or some reference. So each state in this Hilbert space can be labeled as J1 to JC2. So each different possible boundary condition will have a corresponding state in this Hilbert space. Okay, and you have a basis for the bath, which I call gamma K2, and for the black hole you have some state psi K1, and this state is dependent on the boundary condition. Okay, so you need to consider these three Hilbert space and combine the state from these three Hilbert spaces and then take a sum over it. So basically you need three Hilbert spaces to purify the raw reduced density matrix for the black hole. You need the exactly. So that's why it depends on the boundary conditions, right? So you require to add one more Hilbert space, which is the journal Hilbert space. Now the dependence of reconstruction can be thought of as computation of entanglement wedge for the Hilbert space journal Hilbert space, right? So you have a black hole Hilbert space and a bath Hilbert space. You know that if there is no uncertainty in the boundary condition after page time, the bath Hilbert space owns an island in the black hole region, right? The interior of the black hole will be captured by the bath Hilbert space. Now I would like to ask, what happens if I have one more Hilbert space, this journal Hilbert space? Will it capture some portion of the interior of the black hole after some time? Okay, this is what I want to figure out. So the theory dependence of the entire reconstruction will be or can be thought of as the fact whether journal has a non-trivial entanglement wedge or whether the entanglement wedge of journal is a trivial one. It's something which is, it could be living in the scribe plus. Yeah. So that's not the original problem. Yeah, right. The original problem is that if I'm can I read off the interior of the black hole from the H bath? Right. This is the one which contains the radiation, the bath radiation. Now I have one more Hilbert space, the journal Hilbert space. Now I would like to know whether you require access to journal, whether you have to specify a particular state in the journal to read out the interior of the black hole from bath. So that is equivalent to saying that whether do you have a non-trivial entanglement wedge for the journal or not. Sorry? All are? I think you should think of journal Exactly, which is not the path.
And that's like a master state relationship. So it doesn't respond. It has infinitely more degrees of freedom than radius. So it just sets J.
Right. Right.
It doesn't respond to what the path is. So it kind of just sets J.
This is the thing that governs this problem.
Yeah, it's the one that governs this problem. That's how. Yeah.
Exactly.
Something which is much heavier than the path.
Exactly. Yeah.
But you're saying that the Hilbert space won't be effectively disentangled.
It has some entangled.
Right. Each J corresponds to a particular state in the general Hilbert space. So at the end, the entire state of the black hole plus bath can be purified only if I add the additional Hilbert space journal. That means black hole will be entangled with the journal through the fact that there is a randomness in the boundary condition.
I mean, I thought that you specify a probability distribution like that. That's like a classical.
I mean,
There's a state and you specify the coefficients to be the state. So J in the bulk in the system is entangled with J in the journal. Then I specify the state and this is the mod square.
Exactly. Exactly. Yeah. It does have a classical piece, Shannon piece, and then it also has a quantum piece, which is something which we can calculate.
It's diagonalized in this basis.
Right. It is diagonalized in the basis.
It is a density between.
Yeah, you think of it.
Exactly.
Yeah, diagonalized.
So I should think of that like there being some leads come out of the boundary that
Right. Some external thing in the third dimension is affecting. It has infinite number of degrees of freedom because you have infinite number of boundary conditions possible, which is not bath or black hole. Exactly. So yeah, like you said, something popping out of the boundary and it's like keep on.
What they're saying is the journal is a master state relationship. Really, what you could do is you can specify this only at one point of time, right? The state, and then the evolution should take it wherever it does.
Yeah.
So there's some question whether this is a valid superoperator evolution, right? Because you have some system of the black hole plus the boundary condition plus the bath, and you've traced out the journal.
Yeah.
And it's evolving in such a way that this guy is just fixed in time. It's not going to change.
Right.
Is there some consistency condition of whether that's a valid superoperator evolution? There is some consistency condition.
question is in principle there was kind of take any evolution in constraints.
Is it so? Can I just specify?
I mean, okay. So for example, if you preserve the density that phase, for example, you cannot take eigenvalues to be negative. So that is all. Preserve the eigenvalues phase preserving and still possible.
Yeah, but the problem is that these boundary conditions are also interacting with the other degrees of freedom. So the interaction will kind of force them to make sense. Somehow you could use
So directly the CFT1 and CFT2 is assumed to be not interacting at all. It is interacting through the gravity, maybe you can.
This is what I can design a Hamiltonian for the journal Hilbert space so that that interaction effect is very small.
That's what I was asking about the state. So there's still some superoperator constraints conditions.
See, I haven't thought about that.
Once superoperator, the only thing I will check is whether it's phase preserving and maybe that's all. And then it should not make the eigenvalues of the density matrix like negative.
Yes.
And at least there should be a class of initial conditions of the density matrix for which this effective theory is valid. The class of that are within the states which are within the effective theory. Then and evolve, then it should be that the phase it should be phase preserving and not negative.
Maybe the question here is about the operator of limits because if this thing is strictly free, it's just literally free. CFT2,
Yeah.
I guess there's no problem.
CFT2 is literally free.
But if
and then it's not interacting. There is no interaction term that it couples CFT1 and CFT2. It's really free.
Yeah, no, but the gravity is coupling it. Isn't that
Right. I mean, through the gravity, yeah, you could say. Even the dilaton is not coupled to it, because if you couple dilaton to it, then you will be spoiling R equal to -2 condition.
The question is, if it's just an entirely auxiliary system, then it can't affect anything. It must be somehow coupled to the rest of the system.
I mean, through like,
That's
see the.
gravity must be.
I mean, when you compute the state of the black hole by doing a path integral, you have to do a path integral over the matter field and gravity, right? So CFT2 is a matter field. Only thing is that CFT2 can't change the classical geometry of the black hole.
That's a property of JT.
Yeah, that's a property of JT, right?
But it is coupled to the other system through gravity.
Through gravity, yeah. Yeah. I mean, there is no direct coupling in the action, classical action. That's the only thing I'm saying.
It is coupled through.
Yeah, it's coupled through gravity.
Then some of these questions become important. Can you design the Hamiltonians of this?
In fact, what Almeri and Lin did is that they did not assume that there is a bar. They just took this CFT2 that I have here and coupled to gravity, like not through an explicit term in the classical action. Then in that setup, they ask the same question. Do you have an non-trivial entanglement wedge for the journal? So here I'm just extending it to by adding a bath so that I can ask whether it is affecting the entanglement wedge of the radiation. Okay, so like I'm not going to show you this calculations explicitly. This is a setup. Now one can compute the. So the main goal is to determine the entanglement wedge of journal. So I have to find whether there is a non-trivial entanglement wedge for journal or not. So for that, it has to satisfy some constraints. At various times, different systems can have different entanglement wedge, but all those entanglement wedge should make sure that all possible unitarity violations are cured. You are introducing islands to make sure that there is no unitarity violation, right? So it could be that bath has some non-trivial island, journal has some non-trivial island, whatever be like the whoever be the owner of the island should make sure that those islands should like cure all possible unitarity violations.
Page cut for me, like what you cure is just a page. It's not like all.
Yeah, that's additional thing that I will tell you. Like
The whole argument about whether it's in-simple or not is about whether it cures all possibilities.
sorry.
The whole discussion of whether like there is an in-simple or not.
Yeah.
Not was question of whether it cures all possibilities. You don't know whether it.
Yeah, so I have to make sure this is something which I have to see. Like I have to characterize this. What do I mean by this? Right? So what do I mean by this? So it just means that so the entanglement which I compute or get should satisfy all the conditions imposed by unitarity or inequalities. I mean, if I assume that there is a factorization, still I have to make sure that if I have three systems, the strong subadditivity is satisfied.
I thought like there are computations. Same computation is linked to islands and so.
Yeah.
Which show that they don't satisfy all conditions.
No, the generalized entropy will satisfy the conditions, right? Yeah.
No, but other things like the correlation function.
No, I'm not going to compute the correlation function.
What I'm saying is that we know that I thought that we know that the computation that at least this framework cannot actually satisfy all the conditions. Maybe I missed.
I mean, when I state this, I just mean that the entropies that I compute for different system should satisfy all the unitarity conditions like the if you have a system having finite number of degrees of freedom, it should not have ever growing entropy. That's one condition. And the second condition is that if you have three systems, you should satisfy the strong subadditivity satisfied by the entropy of each subsystem.
So basically, you're only putting conditions on non-observed.
Yeah, so right. Only on entropy. So I'm not computing any observable correlation function or scattering matrix and putting conditions on that. Okay.
This is like some discussion we were having also some days ago. Is it sensible to take a quantum mechanical system and just make 1 degree of freedom in it classical? Which is kind of what you have done there. There's a quantum mechanical system which has gravity and so on. And you just take 1 degree of freedom and you just say, this one is just classical exactly.
Yeah.
That doesn't work, right? Because there's no, that is not consistent with linearity. And somehow, unless you allow the journal degrees of freedom to also couple to that, if you just insist that they are just 1 degree of freedom is just classical.
I mean, journal is entangled with the CFT2, right?
Yeah.
And the CFT2 is coupled to gravity, so maybe through that.
Yeah, so as you evolve over time,
Yeah.
you could somehow be forcing the journal degrees of freedom to also interact with that.
I mean, definitely the entropy will be growing. So it seems like there is some sort of exchange happening. Otherwise, the entanglement won't grow, right?
Let me say about this STP and equations portion for the digital will be
Yeah.
But really, you should impose them on the wave function. So they be d-5 minus t on the wave function.
I see.
But here, minus t. But here you can't actually compute t as an operator. You only know expectation of t.
Yeah.
Because this j is entering t.
Right.
So then you can only impose the expectation value of the equation of motion for it.
Yeah.
That's not good enough for quantum mechanical evolution. We really need to know the wave function.
No, actually, I think for this computation of entanglement entropy, I just need to know the background geometry, right? So I'm not going beyond that. I'm just sticking to this classical background and then doing an entropy computation.
I mean, the question is whether the setup is a
Good setup. Oh, that's something which, yeah, whether it satisfies all the consistency or not. Yeah, definitely. Like, I don't know, like, what are the further constraints has to satisfy, like, we can discuss and see even the Almeri's and Lin analysis itself is consistent or not. Even without this path. Yeah, right. Right. So you start with a classical classical boundary condition, and then associated to that, you introduce a like usual technique in quantum information theory. Like whenever you have an ensemble, you introduce an additional Hilbert space.
Just a simple question is that if I have a classical harmonic oscillator coupled to quantum harmonic oscillator, let's say linear, is there any sense in talking about entanglement entropy and all these things for that quantum harmonic?
I see.
It's not clear that all these standard quantum mechanics even applies.
I see.
Right? Because I think it's the same question, right? Because you would have a classical degree of freedom, and then how would you evolve this state? It's not clear. Right? Because you have a classical harmonic oscillator coupled to quantum harmonic.
Yeah. So only way like I could like think of this was that it is actually changing the quantum state. Although it is just changing it. Sorry.
How to write down the Schrodinger equation for such?
So maybe the proposal would be one way to make it work would be, as you say, you make the journal very heavy, so it does somehow interact with gravity. Somehow hold the page, even though the page time is very long. Somehow hold it over the page time, somehow that is significant that we can somehow get away with it. So there's some maybe some slide where you go to this.
Yeah. So even the quantum mechanical system can be then thought of as a classical approximation of a kind of quantum system, right?
Yeah, it's a little worrying because of this pressure of entanglement.
I see.
Maybe there's some way to make it precise along these lines.
Yeah, so naively I was just thinking that journal is a Hilbert space having like infinite number of degrees of freedom, like even powerful than maybe like
behaves the way you want it to behave.
Sorry?
Or if there's a quantum mechanical model of the Jordan,
yeah.
which behaves the way you want it to behave.
Exactly. Yeah. So maybe that's something which I have to like check, even for the Almerian case. So that is a catch.
It's very similar. I also give us a talk with
Mm-hmm.
quantum mechanical system coupled to plastic.
Yeah. So like, let's say if I want to change the boundary conditions, like which is the one thing that you require to define your theory. Like this is a thing which always happens, right? So whether that itself, can I think of this as a quantum mechanical setup? That's the main worry, right? So if I just want to understand. So can I think of this a quantum system? Within that, this kind of a thing is happening, like say in the subsector. So is that a consistent picture? Yeah. Okay, so that may be something to worry about. But like if that, like Ashok was saying, if I can come up with a quantum mechanical setup which actually changes the boundary condition, then like one can ask this in a sensible way, right? So a mechanism, quantum mechanical mechanism that changes the boundary condition, right? So anyway, so like so the computations can be like blindly done if you can calculate the entropy of black hole with respect to time, and you can calculate the entropy of radiation. You can also calculate the entropy of journal. So this involves some correlation functions of twist operators. And this also just involves twist operators, and this involves something called boundary condition changing operators. So this can be calculated, and if I don't care about, if I don't include islands or anything, this calculations will give you the following results. So this will be proportional to, this is a sum of two terms, a linearly growing term and a logarithmically growing term. So the coefficients can be calculated. Similarly, this will be just a linear piece, and here you have a logarithmic piece. So these coefficients, so maybe I can write this as A, B. So initially, this is the way entanglement entropy grows. For large time, the black hole entropy will have two terms, one proportional to like the boundary time, and another is proportional to the logarithm of boundary time, and then for the radiation, it's proportional to linear. It is a linear function of time, and the journal is a logarithmic function of time. Yeah. Yeah, it has delta dependence. I can write down. So this piece will be 2 pi C1 by 3 beta. So B will be C2 by 2 log U beta alpha prime delta square. So if you look at here, like you see that log of delta square, which is just the Shannon entropy piece. So that's a classical part. And here you have the same 2 pi C1 3 beta. So here again, beta alpha prime delta square. Okay. Now the condition, so I said all these entropies has to satisfy the inequalities imposed by unitarity. One is the strong subadditivity. So the step one in this calculation is finding the entropy, calculate the entropy. So this is something one can do by evaluating certain twist operator correlation functions and boundary condition changing correlation functions. once you compute it, you have to make sure that the entropy that you calculate satisfy the strong subadditivity. Sorry? This is beta, the temperature of the black hole. So the step 2 is make sure that since the black hole has only finite number of degrees of freedom, the black hole entropy should be always less than the Bekenstein entropy, which is a constant since you have an eternal black hole. And then you make sure that the entropy S black hole, S radiation, and S journal, basically S of reduced density matrix for black hole and S of reduced density matrix for bath, S of reduced density matrix for radiation, or sorry, the journal, they should satisfy the improved strong subadditivity. Yeah, so this is the quantity that I have to calculate, right? Depending on the way path integral behaves. If path integral is getting a contribution from wormholes, then you have an island contribution. So that's why I'm just thinking of this as the density the entropy for a density matrix. It won't involve any island. This has to be modified, right? Exactly. Below page time, this is equal to just normal black hole entropy without introducing any island. So I'm not replacing it with generalized entropy right now to begin with. So, so what I want to see is whether the thing that I calculate satisfy the strong subadditivity. So let me just briefly mention what is this improved strong subadditivity. This is what I call ISSA. So consider you have Hilbert spaces H1, H2, and H3. Okay, so we can take tensor product of these Hilbert spaces and produce a bigger one, H1 cross H2 cross H3. Now let's say rho 1, 2, 3 is the state of the combined system. And rho ij is the state of ith and jth subsystem. And rho I is the state of ith subsystem. It need not be pure state. So in that case, the ISSA inequality says that S of rho 1, 2 plus S of rho 2, 3 minus S of rho 1, 2, 3 minus S of rho 2 should be greater than or equal to 2 into max of, so you have 3 options. From that you have to choose the maximum one. S rho 1 minus S rho 1, 3 S rho 3 minus S rho 1, 3 or 0. You have 3 possibilities out of which you take the maximum one. So if you are only worried about a strong subadditivity, it just says that the bound is given by 0. So the improved strong subadditivity give you an improved bound. So this is a result proved by Carlen and Lieb, Elliott-Lieb. So one can use this strong subadditivity and check whether the growth of different entropies satisfy these conditions or not. So even before checking the improved strong subadditivity, one has to make sure that the black hole entropy is given by it should be cured, like it should not have any unbound growth. So we have the usual island computation for the black hole. So that I won't be repeating it, but anyway, you can just draw it. So the region associated to black hole can be thought of as this interval with this boundary point, not really lying on the bifurcation point, but on some other point which is close to the horizon, future horizon. And you can calculate you can really figure out what is the value of these points. Let's say this is AL and this is AR. You can compute which value of AL and AR will minimize the black hole entropy. So that can be calculated and see that the generalized entropy for black hole is given by 2 into almost equal to 2 into S Bekenstein for black hole. Okay. The generalized entropy will be saturated, so it doesn't have any unbound growth. So like after U greater than U page, this is what is going to happen. After page 10, you have a constant entropy for the black hole. Now you have to worry about what happens to the journal and the bath radiation. So there we cannot claim that they should have a finite entropy, like they can have unbound growth, because bath and journal have infinite number of degrees of freedom, so they can have an unbound growth of entanglement entropy. So there, to constrain it, you don't have that principle. You have to come up with you have to have a different principle. And so I think it's the improved strong subadditivity that tells you how the islands of journal and the bath is going to be determined. So right after page time, you have to see what is your improved strong subadditivity condition. Okay. So you know that anyway the generalized entropy for black hole is saturated. Now the entropy for bath is given by the linear growth, and the journal is given by logarithmic growth. So it's clear that after U is the boundary time, which has some coefficient also. This is, I mean, I haven't introduced any island. So before or after page time, this is going to be the entropy. For the journal, like it involves computing the correlation function of boundary condition changing operator and then averaging over the distribution. So that actually produces a logarithm. It does have C2 dependence. I'm just. It is growing in time. Actually, whatever correlation function we compute, it actually grows in time, even if there is no bath. Right, but when you compute the entropy, you have replicas, right? When you go from one replica to another replica, when you glue it, you don't have a fixed boundary condition. You have to choose the boundary condition from a random distribution, right? So there it can have a change in the boundary condition when you glue the different copies of the replica. So
this I've not understand. This physically is because you have some system, it's coupled to some journal, and we discussed it at many degrees of freedom,
yeah.
So it doesn't change and so on. But it's just.
But whenever you have a system which is disturbed by any external reference, that can destroy its coherence, right? So that it will be more and more mixtured state. Even if you interrupt that with a classical system.
The state of the journal is not changing, isn't that? Wasn't that the important thing? All you are saying that the journal state kind of doesn't change, stays what it is.
No journal state. I'm not fixing it, right? In the sense that each boundary condition, if it is chosen from a distribution, that is going to be same. But it's always chosen from a distribution. So basically,
rho is fixed, but the state is changing.
Yeah, it's a mixture of states associated with because there's a probability. You're not considering a particular state because a boundary condition is you don't know, it's a random boundary condition. So the moment you go to another piece, let's say when you want to compute entropy using replicator, you choose different copies of the same geometry, right? And each geometry you cannot fix which is the boundary condition because it's drawn from a distribution. So different copies will have different boundary conditions.
That's also replicas in computation.
intermediate computation. Otherwise, physically, I think there is a journal which is keep on.
It's independent of you, right?
Which one?
You do it, the replica computation, you do the computation independent.
Yeah, but the point is that after that you have to do an analytic continuation in time, right? So that if you want to compute the time, entropy for different time, that replica calculation has to be continued, right? The beta has to be continued to beta plus IU. So that time you have your time dependence will come. Any replica calculation is done in that.
So usually in these replica calculations, the dependence as a proxy for that, you take the distance of the radiation. As you push the radiation region out, you see the region. Here you're saying you want to do something else.
No, see as a system, you have a quantum mechanical system which is which is becoming more and more mixed because there is a external thing which is interacting with it. That's the one which is making its boundary condition random, right? So any quantum system, even if you start from a pure system, if you have a external thing which is interacting with it, it will make it more and more mixed state. So that means the entropies just keep on increasing, right? So it's just that decoherence.
At some point, for instance, at u equal to 1, this is the suggestion that the entanglement entropy of the journal is 0.
Yeah, at u equal to 0.
That can't be right because the journal is setting maybe.
That's why I'm saying at what time you are actually starting all this process. Do you want to start it at long back? Then it's fine. Then you change your time to be. Yeah.
At some point, the journal has become disentangled from the system. Then it cannot be setting the boundary condition to be as a function of time. Right? If it becomes disentangled, it's decoupled and disentangled. It's completely wrong. It will never get re-entangled.
No, he's saying that u equals to 1 is the starting.
It's a starting point. Then it's actually just keep on increasing.
Even if u equal to 1 is starting point, then also the.
So the entanglement just keep on increasing, right? That's a calculation.
No coupling. Can you just increase the entanglement?
So you just sorry, if you don't have any coupling, no, there is nothing.
There's no coupling between the journal and the subsystem.
See, the system is starting the entire system with a entangled state, right?
Yeah, but the journal has no coupling.
I mean, you don't have to you don't need a coupling, right? You just so the system, the pure state is an entangled state of the Hilbert is an entangled state in this product Hilbert space, right?
Of the journal and the rest of the system.
Exactly.
The journal there's no coupling between the systems. Then how can you entanglement entropy of the journal?
I mean, classically, it should interact with CFT2. Otherwise, how can it change the boundary condition? At least classically.
So that was something just giving you a reduced to making the state of the system.
Yeah, that's what giving you this summation, right? With this probability square root of pj scale. I mean,
It was a mixed state. Shouldn't we think it's a mixed state?
There could be a statistical, uncertainty.
yeah. So actually, at least whatever I mentioned is statistical uncertainty, right?
It's not the dynamics. So then in the entanglement entropy is enough to give that kind of randomness.
I agree with that.
Yeah.
It's enough to give it, but it doesn't seem identified to the It's a mixed state, and there's no coupling. You can't change the entropy of time. How will it get more entangled or less entangled? Unless you add a coupling.
Now, even if you have a constant classical interaction to any particular system, right? So the
Interaction is not changing.
sorry,
Interaction is not changing.
interaction is not changing.
I don't think you need any interaction anymore. Because you want statistical randomness.
Yeah.
You just want to make them interact and you can decouple.
Right.
It's like that's the best way. Now you
Yeah.
statistically. It's like Schrodinger's cat is a right way and something is after. Now it's just fixed. So there's some chance I'll find it up and down.
Yeah.
But there's no change of that.
I mean, so what I do is I just take this state, define the Rayleigh entropy for it, and then just do a path integral calculation. I mean, is there any like I'm just asking, if I start with this state is fine, right? And find the reduced density matrix for journal. That I can find, right? Now apply the path integral replica computation for that reduced density matrix. Whatever I do, give me a result, right? That is logarithmic. I mean, log of u. I mean, at what point where I'm making a mistake? That's what thing which I want to understand.
So how you're saying
Yeah.
But you somehow continue to do that.
Yeah.
But, and the second thing is that the model, initially we're thinking of just didn't have any coupling, but if it's increasing, there must be some secret coupling between the journal and the rest of the system. Right?
I mean, there definitely it is a matter introduced in the gravitational region, and that matter's boundary conditions keep on changing because of the journal.
If they keep on changing, they can't be completely time independent.
Keep on changing in a sense is not like I mean, J is the function of time.
It is a function.
J is not a function of time. I mean, Ji is not Jiu.
But then how is it changing across the replica?
Sorry.
J is not a function of time.
Because I don't know.
When you go to Euclidean time,
Yeah.
it's also not a function of Euclidean time. Okay.
Right.
So then how can it change across the replica?
No, the point is that where you see so if I consider this state is like it has a time dependence, right? This state, psi, right?
But J cannot change across time.
J is not changing across time, right?
Either Euclidean time or
Right. So, but when I try to,
cannot change across the replica.
yeah, so when I try to get the reduced density matrix for journal, right? It involves inner product of the black hole states, right? And there the boundary condition could be different. When I compute the black hole inner product of black hole states, right? So there so the calculation will be like this. You have, let's say there's a black hole geometry, the disk, and so here I have boundary condition J1, right? Which is a mixture of, so this is a mixture of PJ1 to PJC2, right? And so here you have the row black hole J1 to Jn, right? This row reduced density matrix has this psi in it, right? See, the time dependence is actually coming from the inner product of two black hole states. When I take reduced density matrix here. Sorry, black hole is?
Black hole dynamic forces J.
Exactly. Yeah. So the where I change the bound.
Assumption that J is not a function of time is inconsistent.
Well, I don't know.
No.
I mean, it is possible to have J not a function of time and nevertheless the state change. I think the model.
The state time is a decrease, but there's no coupling. There is a coupling, but there is no coupling.
Well, if it has infinite number of degrees of freedom, right, then it can change and not changing J. J is only some particular combination of those infinite number of degrees.
There must be some coupling then between the
Yeah.
system and the journal.
That is clear. Otherwise, it would not change.
So there's some coupling, but the coupling is such that somehow J still remains fixed in time.
Yeah.
But the coupling changes the state. It's very confusing.
I mean, that's part of the model. I mean, some of the model is telling us that this to achieve this, you must have a coupling. And nevertheless, that coupling is such that such.
Yeah, and
it's like suppose the Young-Mills coupling were very keep it constant, but then you have different values of the Young-Mills coupling. The states will be different.
that's okay. But what has happened now is
But then you're taking a superposition of all those states.
no, then the entropy of the external system would not change with time. This journal is setting the Young-Mills coupling. So there's some more coupling which is actually coupling the coupling the journal to the system.
Yeah, that is the Young-Mills.
So the journal was not coupled, that's not the boundary. Yeah, the journal itself.
I think this is happening because the journal has large number of degrees of freedom, and somehow that allows you to keep J fixed and nevertheless change the state.
So there's some model which is this is okay.
No, actually, see, for me, it's just that if you accept this state, you do the replica calculation, you definitely get time dependence.
Yeah, I mean, in a sense, it's the same log U dependence as in the black hole.
Right.
So,
So yeah. So black hole has some entropy increase.
That one up and this one up. So
Exactly.
So that he's getting from
Calculations, right. Yeah. So the
problem is that part of it is semi-classical calculation and you want to reinterpret it as quantum mechanical.
yeah. So like Right.
It's not completely clear how it's happening in the full quantum mechanics.
Full quantum mechanics setup, yeah. So the only way I can think of it is like Suvrat was saying, if it is a like quantum system which can be approximated as a classical system.
Let's at least have something a little more precise.
Precise, yeah.
Yeah, very not that.
No, they haven't done it, yeah. Bit more precise, yeah. So I understand, like I accept that.
Just think of J, and I think, like, this document suggests that what you're doing and stuff, the boundary you're kind of, like some kind of a local bench in the CPCA. And then you have like some front which is growing into the gravitational region where the C2 is living. And then you just have a log L kind of, entropy of the CM. Is that how you should think about that?
No, I don't know, like the physics.
What I'm saying is there's a universal log L entropy.
Log?
If you take some vacuum,
yeah.
Something, like that, and you calculate that.
Yeah.
Interval L.
Yeah.
Okay. Then you would get something like C log L.
Right. Yeah.
It seems like, if you interpret this C log L as something like that, it seems like there's some L which is going with just like, put a pinch on the boundary and then grows, and then you're just calculating some entanglement.
Yeah, but the only thing is that this journal, like I'm not thinking of this as a part of this black hole plus part. There's an additional external system. It may be computational thing. Right. So anyway, like the dependence is coming through the fact that in the black hole partition function calculation, when I glue certain replicas, there is an interval where you have a particular boundary condition, another interval you have another boundary condition. So to compensate for that change, I have to introduce a boundary condition changing operator. It's precisely that boundary condition changing operator correlation function is the one which is giving you the time dependence. So if you ask me like what is the physical process, I really don't know. Like I don't have a clear model, like Ashok says, I don't have a clear model which how this is interacting and changing the boundary condition. So maybe like that, only then we can, I don't know, like maybe such a quantum mechanical model and then take its classical some limit. Maybe this is just that. I don't know. I don't have clear understanding of that. Okay. So like so after space-time, the one thing that you query is the entropy growth of black hole. That will be a constant, and the path entropy and the journal entropy. Right now we haven't done anything. This is the same entropy that we had even before the space-time. So the path entropy grows logarithm linearly with respect to the boundary time, and the journal entropy is growing a logarithmic function. So now I have to see the strong subadditivity equation, inequality. Then I have to figure out which is the which is the maximum one. So I have three options, right? The S rho 1 minus S rho 1 3 and S rho 3 minus S rho 1 3. So before that I have to say what do I mean by system 1, system 2, system 3. My system 1 is given by the system 1 is journal, and system 2 is black hole, and system 3 is the bath. And I also assume that the rho 1, 2, 3 is pure, right? Because I have a superposition state. So my inequality will be the following. S rho 1, 2 is S rho 2, which is S black hole, S rho black hole, plus S rho 2, 3 is S rho journal. This should be S rho bath. Minus S rho black hole should be greater than or equal to 2 into maximum of S rho bath journal minus S rho black hole S rho bath minus S of rho black hole or 0. So after phase time, the black hole will entropy will be 2 into S Bekenstein. This will be 2 into S Bekenstein. Okay. So after phase time, you see that the bath entropy is a logarithmic, so it's linearly increasing. This is logarithmically increasing. So the difference between the bath entropy and the black hole entropy is the larger one. It's more than 0, right? Because after phase time, the bath entropy becomes more than the Bekenstein entropy. So I have to choose this from these 3 options. So that is equivalent to saying that after U phase, I have to make sure that the S rho bath plus S rho journal minus 2 S Bekenstein black hole should be greater than or equal to 2 into S bath minus 4 into S black hole Bekenstein. Right after the phase time, this is the inequality that I have to satisfy. So this is equal to saying that S rho bath minus S rho journal should be greater than or equal to 2 into, or should be less than 2 into S black hole entropy. Okay, so the difference between the bath entropy and the black journal entropy should be less than 2 into the black Bekenstein entropy. Okay, so this means that this is not, this is a problem, because you have a linearly increasing function minus logarithmically increasing function should be less than 2 into the Bekenstein entropy of the black hole. Okay, so this will be clearly violated, right? Because at U page, so this entropy, the bath entropy is almost equal to the black hole entropy. So definitely after phase time, this inequality is going to be violated. So this says that the entropy growth of black bath should be cured. Right? You have a linear increase in the bath entropy and a logarithmic increase in the journal entropy. At least right after phase time, it looks like the journal entropy is still okay, but the growth of black hole, the bath entropy is troublesome. That will violate this inequality. So to make sure that this inequality is not violated, you have to introduce an island for the bath right after the phase time. So you do the island computation and see that the bath will have an island that cover the interior of the black hole. Okay, so once you do it, you will see that the S rho bath or the generalized entropy of bath will be almost equal to the 2 into S black hole Bekenstein. Okay, so now you can see that at least for some time. So here you will replace it with 2 S black hole Bekenstein. Okay.
What part of the path you take? You take the whole path except for the extreme.
All but?
You take almost the whole path except for the boundary.
Right. Yeah. So here. So this, once you introduce an island, then the inequality will be satisfied, and it just says that the entropy of journal should be greater than 0. Okay. So right after phase time, if you introduce an island for bath, the ISSA will be satisfied, but not for entire time. Then you have to go back and see what happens to the full inequality, right? So full inequality will have a problem again. So this will be replaced by to S black hole Bekenstein, right? So that the second option is 0 now. Now the third option, which is the journal entropy minus the black hole entropy. Journal entropy is logarithmically increasing because that doesn't have any island, right? So it's keep on increasing, and now then it will reach a time at which this quantity will be positive. The entropy of journal minus the entropy of black hole will be positive at some time. So at that time, the inequality changes. Right? Then the inequality will be like this. The entropy of journal minus entropy of the black hole, bath, should be less than 2 into entropy of the black hole.
But this may be at an exponentially large time?
At exponentially large time, a very late time. So for a large amount of time, bath will have the island, or bath will have the interior of the black hole. But there is a time at which this inequality will be changing its nature, so that the difference between the journal entropy minus the bath entropy should be less than the black hole entropy. Right? So that means after some time, the island, there should be a non-trivial island for the journal. Okay, so you can find the island journal, the island for journal, and if you compute the entropy after introducing the journal, the funny thing is that it will be larger. The entropy growth of the journal will be exactly like the entropy growth of the bath before page time. Okay. Now this means if I give up the island, if bath give up the island, bath will get back the same kind of entropy growth. So the entropy growth of the bath after some time, like after this time when the journal will have entropy equal to that of the entropy of black hole, or 4 times the entropy of black hole, at that time, if the bath give up the island and give the island to journal, then the entropy growth of journal and the bath will become same. So that after the time, the ISSA will be always satisfied. So
some system that is like a bar,
yeah,
but its coupling to the rest of the system is very weak somehow. But it has a very large number of degrees.
Yes.
So initially, because the bath is more coupled, it takes over the island.
Yeah.
But if you wait for a long enough time, like exponentially long, then really the journal is the bath because it has more degrees. So then it takes over the island.
Yeah. Right. So that the bath and the journal will start interacting. Black hole will have a finite entropy. Bath and journal will have a link in between. So they will have equal amount of entropy growth. So that means the journal will have the island at late time where the singularity is lying. So only the journal, right? Only the journal. That's a non-trivial thing that is imposed by the strong subadditivity. Like if I don't use the improved strong subadditivity, I won't get this conclusion. So like I said, both journal and bath have infinite number of degrees of freedom. So I cannot use the fact that there should be finite growth of entropy. So I should have something more that constrain a quantum mechanical system which involves 3 subsystems. And improved strong subadditivity is giving you such a constraint. So after some time, so initially there is no island, black hole interior can be constructed. So the picture is like, so let's say this is the interior of the black hole. So this part of the black hole interior can be constructed by using the dual of black hole geometry, the dual CFT of black hole geometry, and after some time you require bath to reconstruct the interior. And at very late time, where you have the singular region of the black hole, you really require the journal. Okay. So I would like to think of this as the fact that the randomness in the coupling or the boundary condition owns the region near the singularity. That means without specifying the boundary conditions, I won't be able to reconstruct the interior of the black hole from bath. If I specify the boundary conditions or the boundary coupling, then I can use the bath radiation or the Hawking radiation to reconstruct the region near the singularity. So you really have, even if there is a tiny uncertainty, so I have this deviation, mean deviation 1 by delta in my distribution. Even if I make this mean deviation almost 0, Still, I have this problem. The only thing is that at what time the journal will own the interior or not. That you can delay by making the uncertainty small and small. If you have huge uncertainty, then even before Bath owns the island, you can own the entire interior. But if your uncertainty is very less, that means, let's say you don't know the UV coupling of your theory, fine details of quantum gravity, still you won't be able to construct the region near singularity. So singularity is sensitive to the details of the theory, unlike the page curve. So that's the thing which that's how I would like to interpret it. But with this catch that whether this additional journal itself has a quantum mechanical meaning or not, that right now is not very clear to me. So here, like the fact that you have a three system and three systems dynamics or the entropy growth is like has to satisfy ISSA. That is the thing which give me this final output. So the ownership of interior of the black hole has to be consistent with the improved strong subadditivity. That's it. Thank you.
Before we thank our speaker, are there like any questions?
So there's this proposal that like time to singularity. Time to singularity.
Time to singularity. Maldacina's computation. Yes.
So they, how is it consistent with what you're saying? Because they say that you can measure the singularity by so like some correlation that was their proposal.
I see.
But you're saying that like even very small uncertainty will eventually take that.
I mean,
so how is that you kind of? You said it was consistent or
I don't know like whether that calculation requires that you have to be within the entanglement wedge. I don't know. So here what I'm saying is that if you require the entanglement wedge for reconstructing anything, then that you can't do if you don't know the coupling. I mean, like page curve is something which I don't really require the entanglement wedge, right? Or I don't really require the details. I see.
At least I think time to singularity they can calculate.
Yeah. But if they specify that this is their theory, like without any randomness, like the moment if you introduce randomness, whether there's a change or not. Usually, let's say you say that your boundary theory is unequal to 4 superangles with knowing all the coupling, then there is nothing prevent you from reconstructing. But the moment you say that the couplings are not known to you, like in the case of SYK, if you're drawing it from a distribution, then you have a problem.
Okay, let's thank the speaker. Thank you.
Thank you.